today we're going to talk about section 8.7 in your book, which is about L'Hopital's rule. We addressed a little bit about what's happening with L'Hopital's rule early on in the school year when we talked about limits and getting the indeterminate form. And the indeterminate form is something like 0 over 0, infinity over infinity, negative infinity over negative infinity, and something new, which would be like infinity times 0. Let me be quite clear with you on what the AP expects. They never ever want to see you write these fractions. And if you do, they will penalize you for doing that. So let's take a look at the first example. This is an old way of doing a limit. And so we're going to factor this. When we factor, if we look on the top, we can actually take out a greatest common factor, and that's 2. And I don't know why I just wrote negative infinity, negative 1. So factor out 2, and we'll get 2 quantity x squared minus 1 over x plus 1. Now the problem is here, the limit of the top is equal to 0, and the limit of the bottom is equal to 0. And that's why we have to create a different algebraic form here. If we continue factoring the top, we're going to have a difference of squares that helps us factor into x minus 1, x plus 1. We have x plus 1 on the bottom, and the nice thing is that we now have a factor on the top that matches a factor on the bottom, and we can simplify what we have. So for all three of these, the top one, the middle, and the end, every time we get 0 over 0, which again, the AP people never ever want to see you write that on your paper. So we'll talk a little bit later on about how we can write it so that we don't write 0 over 0. So we're going to write the nicest form of the limit. If you remember how insistent I was on that from the beginning of the year. Here's the nicest form of the limit. We're now going to be able to substitute the negative 1 anywhere we see an x. So we're going to put a negative 1 there. So we get 2 times the quantity, negative 1 minus 1, which is 2 times negative 2, which gives us a final answer of negative 4. So this is saying the closer and closer this gets to negative 1 from the left and the right, that we are approaching the number negative 4. Our second example, we're going to do the same problem. We're going to do it using division, just to show that there are different ways that we know how to deal with limits. So let's do synthetic here. So on the shelf, you're going to have the solution to the denominator, which is negative 1. We have the coefficient of 2. There's no x term. And then the coefficient, or the constant rather, of negative 2. We're going to drop the 2. Multiply the negative 1 and the 2 to get negative 2. Then you add, not subtract. So we have 0 plus negative 2 is negative 2. Multiply again gives me positive 2. And I'm going to add, and I have a remainder of 0. So this says that the bottom is in fact a factor of the top. So this simplifies. This is now what would be our remainder. This is our constant, and this is the x term. So we've managed to take what we had and to simplify it so that it is now 2x minus 2. When we put in our negative 1 at this point, there is no problem. We don't get 0 over 0. We don't get infinity over infinity or any of those. So we have negative 2 minus 2 is negative 4. And that's the answer that we got for the last time. And now comes what we're finally doing in our lesson, L'Hopital's rule. So L'Hopital says if we have an indeterminate form, that we are allowed to do the derivative of the top divided by the derivative of the bottom. So we're not doing quotient rule. That's not what L'Hopital says. L'Hopital says if you get an indeterminate form, you're going to do the derivative of the top divided by the derivative of the bottom. So here's how we can take care of that 0 over 0. We'll say since the limit of 2x squared minus 2 as x approaches negative 1 equals 0, and limit of x plus 1, should have parentheses, I'm sorry, I forgot those, as x approaches negative 1 equals 0, apply L'Hopital's. So L'Hopital's again says take the derivative of the top. 2 times 2 is 4, so you have 4x. Derivative of that is 0. Derivative of the bottom is simply 1. The nicest form of our limit is 4x, and now we're ready to evaluate that. So we're going to have 4 times negative 1 is negative 4. And so for the third time, we've gotten the same answer for the limit using factoring, division, and L'Hopital's. So example 2 wants us to apply L'Hopital's again. So we need to check to see if we have an indeterminate form. So since the limit of 3x squared minus 1 as x approaches infinity equals infinity is equal to the limit as x approaches infinity of this denominator 2x squared plus 1, we're allowed to apply L'Hopital's. So L'Hopital says do the derivative of the top and the derivative of the bottom. So we have the limit as x approaches infinity of 6x on top of 4x. Looking at the indeterminate form again, since the limit of 6x as x approaches infinity equals infinity is equal to the limit of the denominator, so they're both equal to infinity, so we have that indeterminate form again of infinity over infinity, we can apply L'Hopital's again. So doing the derivative of the top will give you 6, and the derivative of the bottom will give you 4. So we get 6/4 because the limit of a constant is the constant. We can reduce it and get 3/2. Keep in mind for the AP, if you leave this right here, they would give you full credit because it's an equivalent form of 6/4, or sorry, 3/2 and 6/4 are equivalent forms, so they would give you full credit. Example 3, using L'Hopital's, showing this like the AP would want us to show it. We're going to look at the limit of the top and the limit of the bottom. So e to the 2x minus 1, if we put infinity into the x spot, you would get infinity. And if we do the limit of the bottom, the limit of x is also infinity, so we can apply L'Hopital's. Doing the derivative of the top, do not forget the chain rule on e to the 2x. So the derivative of e to the 2x is 2 e to the 2x because of the derivative of that 2x. So minus 0 on top of 1. What's nice about this is that this is the nicest form of the limit. So what we're going to do is stick that infinity into that, and we get 2e to the super big number, and that equals infinity. Example 4 is asking us to do this by factoring first so we can show what we already know. This thing would have an indeterminate form. The top, when you put an infinity, you get infinity. When you put infinity into the bottom, you get infinity. So it has the indeterminate form of infinity over infinity. So let's factor this. The limit as x approaches infinity. Difference of squares on top, e to the x minus 1, e to the x plus 1. On the bottom, e to the x minus 1. We're able to cancel one of the factors on the top and one on the bottom. The reason we want to be able to cancel that out is so that we get the indeterminate form to disappear. We now have our nicest form of the limit. So our nicest form of the limit is the limit of e to the x plus 1 as x approaches infinity. And putting in infinity, you're going to get a super big number plus 1. So you get infinity plus 1 when we put infinity there. So infinity plus 1 will give us an answer of infinity. Looking at this a second way, we're going to look at this using L'Hopital's. So again, you are never allowed to write infinity over infinity, 0 over 0, or negative infinity over negative infinity. So we have to find a way around that. So we're going to talk about the limit of the top. So e to the 2 times infinity minus 1 would be infinity. And on the bottom, when we do its limit as x approaches infinity, we would get infinity minus 1, which is infinity. So both of those equal infinity. We're able to apply L'Hopital's. So that says do the derivative of the top and the derivative of the bottom. Using chain rule on top, e to the 2x times the derivative of the power, which is 2, minus 0. On the bottom, derivative of e to the x minus 1 is e to the x. Now, the nice thing here is that we are able to simplify. And we could have done this in an earlier problem. We could have simplified, and I forget what example that was, but we had 6x over 4x inside, and we could have simply simplified that at this step right here. We could have canceled and said we had the limit of 6 over 4 and not even apply L'Hopital's at that point. So that's a choice that you could make. Simplifying this, we're going to subtract these two powers. So if we have e to the 2x over e to the x, when you subtract 2x and x, you'll get x left. So the limit as x approaches infinity of 2e to the x, because we subtracted, nicest form of our limit. So we're thinking about 2e to the infinity. So 2 times the super big number is that super big number of infinity. Example 5. Looking at this, if we think about what the graph of the natural log of x looks like, as x gets bigger and bigger and bigger, so as x approaches infinity, this graph on the y is also approaching infinity. It's just a super, 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 super slow growing function. So we do get infinity over infinity. Since we want to apply L'Hopital's, we can never say infinity over infinity, so we're going to look at these two. Natural log of infinity is infinity, so as x gets bigger and bigger, y is also, just very slowly. And the limit here of our bottom as x is approaching infinity, it also equals infinity. So this is what one of my favorite people in the calculus world would call an infinity sandwich. And whenever you get this infinity sandwich, sorry, hyphenate that, it means that you can apply L'Hopital's. What is the derivative of the natural log of x? So hopefully you've said it's 1 over x. So we have the limit as x approaches infinity of 1 over x. And then on top of the derivative of the bottom, which is 1. So if we simplify a little bit, we get the limit of 1 over x as x is approaching infinity. So let's think about this. We have 1 over infinity, which is 1 over a super big number. So the bigger and bigger and bigger the bottom becomes, what is happening to the overall problem when you're dividing by that? So you have 1 over 10, 1 over 100, 1 over 1,000,000, 1 over 300 billion. And this means that we are getting closer and closer and closer to the number 0. But as we're getting closer, we're never, ever quite getting to 0. Okay, so example 6 has us looking at the limit now with negative infinity. So as we have x squared over e to the negative x. So what do we want to do there? We want to think about whether L'Hopital's applies. So they did tell us to apply it. So if we apply L'Hopital's, when we look at this, we actually have the limit of the top. So since the limit as x approaches negative infinity of x squared is equal to infinity, and the limit of the bottom, e to the negative x as x approaches negative infinity, is equal to infinity, we can apply L'Hopital's. So doing the derivative of the top, not real difficult. So the limit of the top is 2x. Limit of the bottom, don't forget chain rule, is negative e to the negative x. Now, the same thing happened, or will happen here, that happened up above, is that the limit that we're doing on the top, so the limit of 2x as x approaches negative infinity is equal to negative infinity. And then on the bottom, that limit is also negative infinity, which results in an indeterminate form. And so once again, we're going to apply L'Hopital's. Doing the derivative of the top nicely gives us 2. Derivative of the bottom now makes it positive. But what's nice about this, we now have the nicest form of the limit. We get 2 over e, and it's to the negative x. So when you put in negative infinity, you actually end up with that positive there. So we have 2 over a super big number, and 2 over a super big number is 0. Lastly, example 7. When we look at this, if I do a rewrite on this, we have the limit as x approaches infinity of 1 over e to the x times